Hello everyone, welcome to the manufacturing processes course. In this video we're going to continue the topic that we started before in the previous two videos, which is regarding the design of the sand molds. And we have discussed the first three steps, and in this video we're going to continue the other steps which would need it to have a complete design of a sand mold. And we're gonna start with step 4, which is regarding the code design. In the previous step, basically we have designed and we came up with all the dimensions of the pattern that would be used, and this was just through the pattern design in step 3. So all the details of the pattern, it should be included in a table similar to this one. Once you do the design calculation, and all the dimensions, you're gonna pick them up from this column. Once you finish this column, for any other step, starting from step 4 till the end of the design procedure, basically, if you're gonna pick any dimension from the original product that already given to you in the problem, you have to convert this dimension into the total dimension in the pattern, because from now on we're gonna deal with the cavity itself. We're gonna deal with the original, with the dimension that we just calculated for the pattern. So any dimension, for example, if you're gonna deal with 70 won't gonna be 70. You're just gonna pick the number, the new number that we already found here, okay? So, and it's gonna be clear when we consider an example. But anyway, you should keep in mind, from after you finish this table, any number that you're gonna get from the given problem, from the given dimension of the original product, it should be picked up from this column here, the total dimension, including even the dimension for the core. So what is the core design? As we discussed before, the core is something that we build inside the material here. Like in case that we do have an internal opening, like let us assume that we do have an internal opening inside this shape, like there is a hole here. So to form this hole by casting, we have to include a core. There should be a core built up here, and the core it is basically made of a special sand, as we explained in the lecture before, and it has some additive material should be added to it to give some strength to this core to support or to withstand the pushing that comes and the high temperature that comes because of the molten metal while it flew through the mold cavity inside the sand mold. But forget about the details of the sand of the core for now, and just focus that we may have a core, and this core would be located either vertical or horizontal in the sand or the sand mold during the casting process. So generally the core, it would be any shape, it would be any internal opening, but the key idea, that should be internal. What does it mean internal? It shouldn't be open. For example, if we do have, let us consider the case that we do have a product with this shape. Like let us assume that we do have a cuboid product, and this product somehow have opening here, a hole, like this one. So we're gonna say that this hole, it is internal hole or opening. This opening, it is not necessary to be just a square. It would be any other shape. We may have, for example, a product like this one. This is the product, and the opening, it has just a square shape. Still, we still gonna use a core for this opening. This also still an internal opening. So for these two openings, basically, we have to use for this ones, we will use core to create them during the casting process. Make sense? So this is the basic idea of the core, as we discussed before. And as I mentioned, the core, it would be vertical, it would be horizontal, it would be located in the casting horizontal or the vertical. There are a little bit or some differences that should be considered, whatever it is, horizontal, vertical. But anyway, we're gonna discuss this one, and it's gonna be clear as we cover more examples in the next videos. But for now, we'd have either two options for the core. It would be either horizontal or vertical. But there is another point that I'd like to demonstrate here. How about if we do have a product with this shape? that this is the product. So as you can see, there is like not opening, actually it is like something like a cut of the shape, like something it is incomplete opening, like this opening it is not surrounded by metal everywhere. The metal, this is the metal part, but there is nothing here. So if we decided to form this opening, this cut from in this product here, there is no need to use a core. You can use a core, yes, but there is no need to use the core. Why? Basically, if you just form the pattern, we said that the something that form the mold cavity is the pattern. So I'm gonna assume that the pattern is gonna be typically the same shape. So you're gonna end up with a cavity. The cavity is gonna be seen, and you're gonna have like a little bit projection of the sand. There should be like a little bit projection of the sand for this portion here. Will be projected of the sand. Consider that this is the sand. All of this part is just the sand. All of this just sand, 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 sand. So automatically this portion, this cavity, this part, this feature will be automatically formed using this projected part of the sand. If you try to merge these two parts together, we already can form this opening. So we're gonna say that this opening, it is not internal opening, and there is no need, no core will be used for this one. Okay, so the core basically we're gonna use it in case that we do have an internal opening, and this opening is surrounded by a metal from everywhere. But this opening, it has metal from one side, and that is fine. We can form the sand. This is gonna be the sand itself. We can shape the sand itself in this form, and in this case, this portion, it is not a core. This portion, it is not a core. This one, this portion is not a core. It's just sand. It is just the sand of the mold itself. Make sense? So as I mentioned, the core, it would be either horizontal core, it would be either horizontal core, it would be located horizontal, or it would be either vertical core. So as we agreed before, that the core, to be supported standing in the sand or the mold cavity, in other words, it requires core prints. So what are the core prints? These core prints are something that give a support to the core to be standing in the mold cavity. Because the core inside the mold cavity, it should be surrounded with nothing. There is nothing around the core inside the mold cavity. So if there is pushing comes from the liquid metal inside the mold cavity, it's gonna push the core, and it's gonna give like a little bit shift or displacement, or even it's gonna make the core fall down, or especially if it is already standing vertical inside the mold cavity. So we do have difficulties here. So to avoid the displacement or moving or the push, to give a support to the core, again, if the pushing comes from the molten metal, we should provide some core prints to the core itself. So the core, it's gonna be, if we're gonna talk about the core itself, assume that the core, it has cylindrical shape. So this is gonna be the core, and it has typically the same shape as the hole. Like let us assume that this is the hole, so we're gonna have a core with the same shape, typically the same, but the difference will be in the dimensions. So what we're gonna do, it's gonna have like typically the same shape in case, and it's gonna be located horizontal as drawn here. As we mentioned that the core by itself, it won't gonna work. It requires some support. So that's why we're gonna add here to the core some core prints, right? So we're gonna have one core print on the left, and there is another core print on the left. And you should keep in mind that the core, with the core prints, they are made as a single object. Like the core itself, it is not just the portion that is corresponding to the hole itself. No, the core is everything. All of this is just the core. The core is all over. This is all over a single object made of the same sand as a single object. This is gonna be the core. But you should understand that the core itself is just this portion. And these extra portion are made as core, are included at the core print. So this is the core print, this is a core print, and there is another core print here. Make sense? So if the core is already located horizontal, this is an option in the casting. So we're gonna add here the length of the core print. We're gonna refer to this length as I, and I'm gonna let you know how we can find this I dimension. This should be the length, and this length basically depends on the overall length of the core. This should be the core length, and it depends also on the average diameter of the core. It depends on the diameter of the core itself. So to find I basically for a core that is gonna be located horizontal in the sand, this I you're gonna find it from this table. So that's why I'm including this table here, right? So this I is gonna be this I. This should be the I that I'm talking about, right? This should be the I. Okay, it is already I, but in lowercase. So let us assume that this is the I in uppercase. So this value, this number, you're gonna pick one of these numbers to give the length of the core print for the core in case that it is already located horizontal in the sand mold. But the other option that we may have the core itself, it would be located vertical. Like in this case, we're gonna have a core that is located vertical in the sand mold. So the core in the vertical direction, it's gonna have the same shape. And again, as we mentioned, we are going to add to the core some core print. So we're gonna add one core print on the top, and there should be another core print blue in this way. Okay, it is already located vertical, and again the core print is just a single object. All of this is just made of the same sand, the same way, all of it just a single object in this way. But the exact core portion is going to be this part. This part is going to be the length of the core. This should be the length of the core, and there should be the average diameter. This should be the D of the core, the average diameter of the core. And if we're gonna look here, we're gonna find that there should be like an extra projected portion for the core print up and down. So this should be the core print as well, and this portion, it should be the core print as we discussed. So what is the height here? The height is gonna be H1, and the height of the core print, the upper core print, so the blue core print will be H1, but the upper core print, this height, it's gonna be, we're gonna consider like 0.6 H1. 0.6, this is like a fixed fraction, like it is 60% of the height of the blue one. So this is where it's gonna be located. Like why we should have the core print blue bigger, or the lower core print, it should be bigger than the upper core print, the core print on the top, and this is the core print down here. Why this H1, it should be bigger, or this lower core print, it should be bigger than the one on the top? This is because that it is located vertical, so all the weight of the core print, it should be supported by the lower core print, so that's why it should be bigger or have longer length to give more support. But as for the top one, the support that comes from the top core print, it is not essential like the one located lower or blue in of the core print. It makes sense. So that's why we are taking just a fraction of the total height of the lower core print, which is H1. So this H1 value, we're gonna find it from the table. So the key idea here, it depends on the orientation of the core print in the sand. The core print, the core itself. The core, it would be horizontal, so you're gonna add I and I. And it means that the two core prints, they should be equivalent of the same length, and the length I and the length of the core print will be I, and this I, you're gonna find it in the table, and I'm gonna let you know how we can find I for a specific core from the table. How about if we have the core as vertical? So in the vertical orientation, the lower core print, it should be bigger than the top core print. Why? Because most of the weight and most of the support comes from the lower one, because it is located vertical. So the essential support comes from the lower core print, and the top one, it just give some auxiliary support to the core. So that's why all the H1, it should be, if it is H1, it is acceptable to have like 60% of H1 for the top core brand. Make sense? So, and this 60%, there is a fixed value. This is practical value or empirical firm value that we already got from the practical use and from the experience, that basically we are using 60% to give a support to the, a good support to the core prints. So how we can find H1? Again, we're gonna use also the table. As you can see, there is another column for the H1 here. So you're gonna pick one of these numbers to be given for the H1, which is the height of the lower core print in the vertical core, if in case that is already located vertical in the sand mold. The question is how we can find I or H1. It depends on it is horizontal or vertical. We need two information basically. We need the length of the core and the average diameter of the core. How we can find these values? Basically, the length, intuitively, the length of the core and the diameter, they should be the same diameter and length of the opening. Like assume that this is the diameter of the hole that you would like to form by casting. So this should be the diameter and this should be the length. But the question is, this should be the diameter of the hole and this the length and the diameter of the hole. So does the diameter of the hole is typically the same as the diameter of the core? Or the diameter of the core is the same as the diameter of the hole? Because the diameter of the hole will be given. The length of the hole will be given in the original. As I mentioned, we agreed that the given information, you will be given all the details and the shape of the final product. So if this is the final product and the diameter is already given of the hole and the length of the hole will already given, intuitively that the diameter and the length of the core, they should be the same diameter and the length. But they should be the same diameter and the length of the core that should be located in the mold cavity. And as we agreed, once you finish this table, any dimension that you're gonna get or pick from the original product, from the final product, it should be converted into its equivalent value. So what you're gonna do basically, you're gonna look to the final product. And for example, if the diameter of the hole here it is 50 millimeter, so you're gonna go to the table C or 60 millimeter, you're gonna find that the 60 millimeter should be another value. So this value will be the exact diameter of the core that you're gonna use. So what does it mean? The diameter of the core, the length of the core will be the values that you have to, for the hole diameter, the length of the hole of the opening of the original product, but you're gonna get them, these dimensions, from the last column in the table in that of the pattern dimensions in the steps 3, right? So you just translate the or convert, find the exact value. You're gonna pick the diameter of the hole, and which is gonna be the diameter of the core, the length of the core from these values, from this column. Then you're gonna use the diameter of the hole. You're gonna move here. This column gives us, you're gonna pick the diameter of the hole. For example, let us assume that we got the diameter of the hole equals, let's say from the table, we got it like 67.5 millimeter. And the length of the hole, we got it like 158 millimeter. So what you're gonna do, you're gonna take these two numbers and move to pick either I or H from the table, depending on the orientation of the core. Is it horizontal or vertical? So the diameter it is 67.5. What is 67.5? This is the diameter. Is it up to 20? Is it less than 25? Up to 25? No. Is it between 26 to 50? No. Is it between 51 and 100? Yes. So this is the row. So you have to pick one of these numbers in this row. Then you're gonna use the core length, which is 158. The core length right now, it is 158. Is it up to 50? No. Is it less than 50? Up to 50? No. Is it between 150, 51 up to 150? No. Is it between 151 up to 300? Yes. So you're gonna have two numbers here. One is for H1, the other one is for I. These two numbers, they are not necessary to be equal, as in this case. They would be equal, they would be different. Like this case, it is 100, here it is 90, here it is 35, here is 40. It doesn't matter. Just you do have two numbers. But the question is, which number that you have to pick for this case? This basically depends on the orientation of the core. If the core is oriented horizontal, you're gonna pick the I number from the table, and you're gonna consider that the length of the core is gonna be 50 here, which is I, and there is another 50 here. But in case that the core print is oriented vertical, so you're gonna pick the other number, which is also 50 for this case, but as I mentioned, it would be a different number. So you're gonna pick the H1 value, and instead you're just gonna skip the I and just gonna focus and pick the H1 value. Then H1 value, you're gonna add it here. You're gonna consider that H1 here is gonna be 50, but this one is gonna be the 0.6 times 50, which is 60% of the 60 of the 50, and then you can calculate this value. This is gonna give us the height of the core print on the top. Make sense? So this is simply how we can find the core print dimensions in addition to the length and the diameter of the core. The length and the diameter of the core, you're gonna find them from the table, but as for the dimensions for the core prints, you're gonna find them from this other table that is already will be given here. Make sense? So this is for the core print design. The next step is step 5, which is calculate the gross weight of the casting. So what is the casting again? The casting, this is basically anything that have a cavity inside the sand mold. Like for example, as we mentioned before, so if we're gonna look to a typical mold, a sand mold is gonna have all of this. It should be cavity that should include this cavity will be filled with the molten metal that is gonna give the final product or the casted product at the end. But in addition to this one, we're gonna add some opening for the riser, and there are some other openings for the gating system, like the core, the boring cup, the down sprue, the sprue well, the runners, and so on. So when we fill these cavities with molten metal, and then we're gonna leave it for a while till solidification, as we mentioned before in the procedure of the sand casting process. So all of this area, all of this region will be filled with molten metal, right? So the objective right now is to figure out or find or calculate through this step, and this is the objective of step 5, is to calculate the weight of this casting, the calculate of this molten metal, how much it weighs. Okay, so this is the objective of the step 3. Step 3 simply is just to find the gross weight, the overall weight of not just the product. This is not the product. We are getting the overall weight of the casting, of the molten metal that should be poured inside the mold cavity. Why we need it? Basically, we need it for the boring time calculation, for so many other calculation. What should be the temperature that we have to heat the molten metal to? In addition, we're gonna use it definitely, and it's gonna be seen in step 3 for the calculation of the gating system. Okay, so that's why in step 5 we are calculating the gross weight ahead, and we will use this gross weight value for the calculation or the design of the gating system in step 7, right? So in step 5, simply calculate the gross weight. The gross weight, which we're gonna give it a symbol as G. We're gonna give it a symbol as G, stands for the gross weight of the casting. Again, this is not the weight of the product, this is the weight of the casting itself. The gross weight, it should be 1.3. It can be approximated as 1.3 times rho times m. Times m, where m, this is m, this should be the mass of the cast. What is the cast? This is anything, the product itself. This is the metal that is gonna fill into the mold cavity. This is just the cast, which is this thing that is gonna come out of the sand after we trim and clean the sand and after we trim the gating system, the riser and everything. So your objective is just to calculate. So how we can find this gross weight? Simply, what you're gonna do, calculate the mass M. What is M? This should be the mass of the cast itself. And then you're gonna multiply this mass times 1.3. Why 1.3? It means that we are like increasing 30% of the mass, and this 30% is gonna be added to include the mass of the gating system, the mass of the riser as well. as I mentioned, that here in this step we are interested to calculate the gross weight, the weight of all the molten metal that should fill into the cavity. But the cavity, it is not the cavity for the product, not the cavity for the cast itself. There are some other cavities that shall be filled out with molten metal. These cavities will include the gating system in addition to the riser. So the gating system and riser, this contribute nearly to 30% of the gross of the overall weight. So that's why we're gonna calculate the mass of the cast, and then we're gonna multiply this mass times 1.3, which it means that we are increasing 30%, this 30% for the riser and the gating system weight. How we can calculate the mass of the cast? As you know, the mass of any material, of any body, the mass generally relation from physics, it is rho times V. What is rho? This should be the density. This should be the density of the metal, of the cast. Like for example, we're gonna do casting from steel, so this should be the mass density of the steel. If it is from copper, so it should be the mass density of copper, and so on. Anyway, in most of the cases it will be given, but you should know it is commonly known value for that the rho for the steel, the density for the steel, it is 7.8 grams per centimeter cube. Make sense? And what is V? This should be the volume. This should be the volume of the cast. So your objective basically is just to calculate the volume of the cast, multiply times the density, you're going to end up with the mass, multiply times 1.3, you're going to end up with the gross weight. And remember that the gross weight, this includes the weight of the molten metal inside the mold cavity itself, plus the molten metal that is going to cover the or fill into the gating system in addition to the riser. So this is the gross weight that of molten metal that should be included or added or fill into the mold cavity. And this value of the gross weight, you're gonna get this one from the calculation. Basically, we can find this one in terms of grams or kilograms, depending on the unit. So the gross weight here, it should be like the gross mass. To be more accurate, it should be the gross mass. It means that we are interested to find the G, and then we're gonna use it again later for the calculation or the design of the gating system. Make sense? Now let us move to step 6, which is just to find the dimensions of the flask. We said that the flask, this should be the metallic box that should be open from the top and blue, and it's gonna be filled with sand. And we basically inside this box, this metallic box, we shall form the sand mold itself. So the flask, which is mainly, it would be made of cast iron. And in many of the cases, or it would be made of wood for simple castings. But anyway, forget about the material and just focus on the dimensions of the flask itself. So to come up with these dimensions, basically, we have to figure out the arrangement, like the front view and the top view, how it's gonna look like the flask itself. So basically, the flask that we're gonna consider through this course, as we agree, is gonna have two parts. The top part is gonna be the cube, right, and the drag, which it should be the lower part, right? For the cube or the drag, basically, what should be the dimensions in terms of length, in terms of height, in terms of as well the width. So these are basically three main dimensions that we are interested to figure them out or find them for the flask: the height of the cube and the height of the drag, and the length and the width of the flask. Make sense? So how we can find these three main dimensions? Basically, you should set up or draw the mold kind of and set up all the dimensions. And these dimensions, like what should be this maximum dimension, what should be the maximum height above the parting surface, because this should be the parting surface here, what should be this maximum height, for example, this distance, how much it is. So all of these dimensions, you should arrangement or distribute them for the casting. How we can find, or from where we're gonna find these dimensions? All of these dimensions, you're gonna find them in this table that as I mentioned, that once you finish the table of the dimensions of the pattern, any dimension you're gonna find all the dimension, we're gonna find them in this total dimensions column. So we're gonna find these dimensions here and we're gonna arrange them as I'm presenting here, like what should be this height, how much is this height, how much is the height of the core print. We agreed that this core, because this should be the core print, this core is arranged vertical. And we agreed that this height here, it should be the H1, and this height, it should be the 0.6 H1 as we discussed above for the core print design, right? So these vertical dimensions, we're gonna find them in addition to the maximum dimension, how much is the maximum horizontal dimension. So this should be, this view, it should be the front view. This should be the front view, and we should have here the top view as well. If we try to look to the casting from the top view, we're gonna find that this, if for example, assume that this casting has cylindrical shape, so it has, that is fine just to draw the big circle. I'm care about the bigger dimensions. I don't care about all the details that you shouldn't add all the details in this views or this representation, but just the maximum horizontal dimension, the maximum vertical dimensions, or the essential vertical dimensions, what they are. In addition, for the top view, for example, if it has circular projection here, so how much is this diameter, which it should be the same diameter that already represented up there, which is this diameter D. Make sense? Once we find these dimensions, and anyway, this dimension, you're gonna just bring them from the table in step 3, right? And in addition to these dimensions, there are some other dimensions that you should consider for the gearing system. Like, for example, we're going to have here the down screw, and this should be the boring cup. So at this parting surface here, how much is the diameter? As we agreed before, that the down screw should be tapered shape. It means that it will have a diameter from the top, which is bigger than the diameter from the blue, which is the lower part of the down screw. So if we try to figure out if we try to slice this front view from here, and we're gonna have a sectional view, so we shall find here, we're gonna find and just get rid of the cube. It means that here we are representing the top view of the drag itself. We don't care about the cube for now, the cube for now. It means that this diameter here, this DS, this stands for the diameter of the down screw, which it should be the smaller diameter, not the bigger diameter. So this is the small diameter at the bottom here, not the diameter at the top, right? So we're gonna say that this should be the DS. The diameter here, it should be the DS. So there should be a diameter of the down screw, and this extra portion will not be shown since you already removed the cube and just looked and represent the top view of the drag itself. Then there are some extra dimensions like A, and there should be B, and D and B from here. So these dimensions, basically, you're gonna arrange them in the front view and the top view, and these dimensions you're gonna find them in a table. We're gonna find them from a table. So for example, in the front view, from the highest point, including even if there is a core print, from the top of the core print or from the top of the molten metal, it means that the highest point above the casting itself, you're gonna arrange or you're gonna include a dimension. This dimension should be A. We're gonna give a name to this dimension as A. And this A, it should measure the length of the column of the sand, because what is above here is a sand. So we are interested to figure out how much is the column or the height of the sand above the casting, above the mold cavity, right? So why you are interested? Because we should set up the mold cavity with a suitable strength, that the sand or the sand of the mold should be strong enough to support the pushing and the weight and the buoyancy force, as we discussed before, that comes from the pushing from the liquid metal, right? So it means that this sand, if it is short, it won't gonna able to support this pushing. It means that after a while it's gonna break down, or some cracks would show up. Make sense? So what does it mean? It means that this sand, it should be with a suitable length, and this A, it shouldn't be short. How we can find this A? There is a table that from which we're gonna bring a value for A. Make sense? the same idea here. Down the column of the length of the column of the sand below the casting, it should be also A. It shouldn't be less than A. It should be bigger, that is fine, but less than A, it is not acceptable, right? To avoid the cracking of the sand. The same idea works for the top view. From the top view, for example, how long is what is the length of the sand that should be on the side? Because here we are getting the sides of the sands. How long should be these sands, the sides of the sand column or the sand surrounding the casting, because there should be some liquid here, so there would be some pushing everywhere, right? So to avoid this pushing, basically the sand, it should be with a suitable size here. This is the size of the sand, because there should be sand everywhere. So this length, it shouldn't be less than B. This one should not be less than B. And the same thing. So all of these dimensions, it shouldn't be less than B. How much is B? We're gonna find it from a table. But as you can see, there should be a little bit small column or part of sand here that is gonna be located between the bottom of the down sprue, or the lower part of the down sprue, and the casting itself. This dimension, it should be D. How much is D? We're gonna find it from the table. So this arrangement of the dimension is fixed. Like what you're gonna do, you're just gonna set up the casting inside the mold, inside the flask, and you're just gonna add these dimensions A, B, and arrange these dimensions in addition to D, as shown here in a figure for a given example of a casting, right? Then your objective basically is just to calculate somewhat how much, what should be the length, how long, how much is the L, how much is the W, which it should be the length of the casting, the flask, how much is the W, which it should be the width of the flask, and the length and the width, you're gonna find them from the top view, but from the front view, you're gonna find the height of the cube. This should be the height HC. We're gonna give it C, where C stands for the cube. Make sense? So we are interested to figure out how much is the height of the cube in addition to the length and the width. Make sense? HC. So for example, if I ask you from this table, if you just read the table, how long should be HC? So HC, from, if you just gonna calculate it, it should be this total height, which it should be this height. Let us assume that this height, like for example, forget about H1, like Q. Okay, so if this height Q, where this Q should be like a number that you're gonna find from the table in step number 3, and you're gonna add 0.6 H1, and H1 you're gonna find it from the table. We already got it in step 4 for the core design, and plus A, this is gonna give us HC. So HC is gonna be A plus Q plus 0.6 H1. These two numbers, we already have them, but we have no clue about H. What should be the minimum column of sand above the casting to avoid cracking of the sand itself? We're gonna find this A from a table. How about the length? If I ask you how much is the length of the flask, the length, it should be B plus ds. What is ds? This is the diameter of the down sprue, but we didn't calculate this diameter yet. Plus d plus the big diameter, the uppercase diameter, which it should be the diameter of the casting, and this diameter we're gonna find it from the table in step number 3, plus b. So the L here, as you can see in the figure, it should be b plus d plus ds plus big D plus there is another b, right? So as you can see, if we sum, we're gonna end up with like 2b plus d small plus ds plus bigger D, which is this dimension. We're gonna find it from step 3, but this one is not calculated yet. We have no clue how much is this ds, but these two values b and d, will find them from table. We'll find them in the Flask table. So what is the Flask table? This is gonna be this table. From this table, you just gonna use the mass of the casting. What is the mass of the casting? This here, you're gonna use the G value. What is the G value? This is the gross weight that you calculate, or the gross mass that you calculated above. But make sure that this G should be in kilograms. So if you did the calculation and you got G in terms of grams, you have to divide by 1000 to convert into kilograms. Then you're gonna ask yourself, is G up to 5 kilograms, or between 5 to 10, or 10 to 25, or 25 to 50, or above? So you just gonna pick, for example, we'd have 50 up to 100, 100 to up to 150, and so on. So the column continue here, like we do have 25 to 50, and we do have 50 up to 100, 100 up to 150, 250 up to 500, 500 up to 1000 kilograms, right? So this is a very huge, it is 1 ton casting. It is a big casting. For bigger casting, even we can use the same dimensions basically. So this is gonna give us A, B, C, and D. What is C? C is not, we didn't include C here, right? In these figures, but from this table you're just gonna bring the value for A, B, and C from the table depending on the G, which is the gross mass of the casting itself. Then, so from the table we already got A, and we already have values for H1 and Q, so simply you're gonna sum these data together, you're gonna end up with H1, the same thing for L. But the problem with the L, basically, we have no clue how much is DS. DS, this should be the diameter of the down sprue, and this diameter we're gonna calculate it in the last step, or at the end, which is the step that is gonna be used for the gating system design. But we didn't calculate this DS for now. So what does it mean? From this step, you're gonna find L is a number plus DS. You're just gonna find it, right, the L for now through this step as a function of DS. Till you find the DS at the end, then you're gonna substitute with this value here to find the length of the flask. How about the W, the width? The width is gonna be the same. If you just gonna sum, the width is gonna be B, and there should be D, which is the diameter of the casting, plus another B. So we're gonna end up with 2B plus D. And this D, you're gonna find it from the table in step number 3, but this one we already got it from this table here for the flask dimensions. Make sense? So this is it for this step. Your objective is just to draw these two projections of the casting, of the mold, of the sand mold, and arrange or distribute the A, B, and C and D dimensions, and sum the total height of the cube, the total length, and the total width. If we are interested in the height of the cube, for some cases, we can even calculate the height of the drag, we can calculate the height of the drag as sum these dimensions plus A, you're gonna end up with the height of the drag. But in terms of the calculation, for the next calculation, we need the height of the cube. So that's why I didn't calculate the height of the drag, but you can do the calculations. And another thing that I'd like to mention here, in some cases, for example, in this casting, you're gonna find that the height of the cube is different than the height of the drag, right? But how about if you decided to use the same height for both? Like it depends on the availability of the flask that you have in the foundry that you're already working in. How about if we do have the flasks that they should be identical, like the cube and the drag are identical, and I should use the same height for both of them. So your objective is just to calculate the height of the cube, the height of the drag, and you're gonna use the bigger one, the bigger height for both of them. But if that is fine to have different heights for the cube and the drag, and you can use different flasks, no problem. And this again depends on the availability of the flasks in your foundry. So in this case, you can give a different value for the cube that is different than the height of the drag, no problem. But anyway, for the calculation, we just need the height of the cube itself for the next calculations. Okay. Once you do the calculations for the height and the length and the width, for example, you may end up with some number, like you may end up that the height of the cube is 50.7. So there is no flask with 50.7 millimeter height. It means that you have to pick standard, or you have to pick a suitable height flask with a sweater with a height that is equal to or bigger than the HC that you already calculated. So what does it mean after you do the calculation? You have to convert it into a standard value, or a value depends on the availability of the flasks in your foundry. The same thing for the length and the width. So what are the standard values for these, for the H and the dab and the length and the width of the flask? These are the standard. That the H started with 10. We don't have a flask. We may have a flask with 10 millimeter height. We may have a flask with 20 millimeter height. We may have 30 millimeter height. But for example, if you did the calculation and you found that we do have an HC, you got it from the calculation. This H stands for HC or H drag, any height for the drag or the cube. This height of the flask, basically, if you got it from the calculation like 23.5 millimeter, there is no 23.5. So your choice, you have to use a flask with 30 millimeter height. But the 20 millimeter height, it won't gonna work. Why? Because it's gonna result in some cracks. It means that the flask is short and the column of the sand above the casting, it is short. It means that it will be cracked. So you have to pick the next higher height of from these standard values. So the standard values of the height, it works like 10, 20, 30, 40, and so on up till 100. Beyond the 100, you're gonna have one jump up to 120, then 150, then 200, 250, 300, and you're gonna move with a step 50 millimeter till infinity, for example. I mean forever. And if we're going to talk about the length and the width, it's going to be the same. The standard are the 50, 100, 150, 200, 250, and so on up to 500. Beyond the 500, you're going to have 100 step. So it's going to have 500, 600, 700, 800, and so on. Make sense? So these are the standard. Your objective is just to calculate H. Once you calculate HC, L, and W, you're going to pick the next higher standard value, higher than the value that you already got from the calculations here. Make sense? This is how we can calculate the flask dimensions. And the next step basically is to calculate the gate or the in-gate diameter. Go to the design of the gating system. The gating system, this includes different elements. If we gonna know this is a typical shape of the gating system, we do have here the coop. This should be the boring cup. This should be the boring cup. Then we should have here the down sprue, and there should be the sprue well, right? And this should be the runner. This is the runner itself. And we said that this a little bit small opening that directly gonna feed the metal into the mold cavity, because this should be the cavity. This should be the mold cavity. Okay, this a little bit small opening, this is the gate that I'm talking about here. So through this step, which is step 7, we are interested in finding the area of this in-gate or gate. It would be called in-gate, gate, or in-gate. And we are interested in finding the diameter. So to find the diameter, it means that it's gonna be circular, and in many of the cases we are forming the in-gate or the gate as circular shape, and it has a specific area. So the area of the in-gate of the gate, it can be calculated using this formula. This is this formula basically we got it from the Euler-Bernoulli equation of the fluidity and of the molten metal to achieve laminar flow. So don't forget about the derivation of this formula for now, but let us go over the different terms here. So this should be the area of the in-gate. This is the in-gate area or the gate area. G, this is the gross mass. What is the gross mass? This is the mass that you already calculated in step 5. You calculate the volume of the casting, you multiply time you find the mass, then you multiply time 1.3 to end up with the gross weight. So this should be the gross mass or the gross weight here. And rho, this stands for the density of the molten metal. As we mentioned, for example, for the steel, it is 7.8 gram per centimeter cube. So this should be the density. T, this is the boring time, and we're gonna give a little bit talk about the boring time. This is the time that you have to spend in pushing the liquid or boring the liquid, not pushing basically, boring the liquid into the mold cavity. As we discussed before, during the casting process, that we basically gonna have a molten metal, and this molten metal is gonna bored into through the gating system to fill into the mold cavity. And we said that this boring, the boring process itself, it should be controlled. So what does it mean? It means that you should allow for a laminar flow, for an easy flow of the molten metal through the gating system. Because if we have a turbulent flow, this will trap some and bring some air and trap this air inside the mold cavity, and this would result in some defects in the mold, like the porosity as we discussed before. So we should achieve a boring laminar flow, and this will achieved through the control of the boring time. The boring time, it shouldn't be too short, it shouldn't be too long. It should be optimum to achieve a better casting, as we are going to discuss. So the boring time for now, it is S times the square root of G. This basically in case that we do have steel. This is for steel casting. For other casting like cast iron or aluminum, you may have a different formula, but this is a very common formula for steel castings, like it's gonna be S square root of G, where G again, this is the gross mass, and S, this is just a constant that depends on the fluidity and the viscosity of the molten metal. So it is a material constant that is commonly used as 1.5 for steel castings. And mu, this is another constant here that basically depend a lot on the coefficient of friction between the friction between the molten metal and the sand during the gating system itself. And basically it's gonna be given, or you may have you can assume this one like a factor like 0.3, 0.4. It depends on the how, and basically we identify this value based on the experience and based on the size of the casting, the type of the sand that we're already using in the foundry, in addition to the type of the molten metal that is going to be poured through the gating system. G, this is the gravitational acceleration, which should be 9.81 meter per second square, or 32.2 feet per inch square in case that we are working with the inch system or the American system. But here, as you can see, that all the units that we're already using are in the metric system. H, this is the effective height. What is this effective height? This is the head above of the molten metal above the parting surface. So this effective height actually can be calculated as H negative B square over 2C. What is H? This H basically, this should be the height. This H is the height of the cube height. This should be the cube height, which it should HC. That's why here we are basically interested in finding the cube height, which is HC. And as for the drag, if you would like to calculate that, is fine. If not, you aren't gonna use it for the next step, but for sure you're gonna need it for the design, the real design of the flask itself, right? But basically for the next steps, we need just HC, which is the height of the cube. So that's why this is gonna be H, which should be the height of the cube, negative B square over 2C. What is this 2C? This 2C, this is the one in the table here. But you can figure it out from the physical one. Don't use the same C here in the table, but use the C that is gonna be given. What is C basically? This should be the height, the total height. The C should be the total height of the casting, the vertical height of the cast or the mold cavity. So C, this should be the height as represented here in the figure. So for example, this is the cavity. Here, this is another cavity. The cavity is given in this way, and there should be this dashed line. This should be the parting surface. So we're gonna have here this red line. This is the parting line surface, where it should be located, the parting surface. And here we should have the parting surface. And as well, we should have here, this should be the parting surface. Should be located here. So the C, this stands for the total height of the casting. C stands for the total height of the casting, total height of the casting or the mold cavity. But what is P? P stands for the distance from the highest point above, or the height of the molten metal, the height of the molten metal above the parting surface. So again, P, so I'm gonna write down, write P here. So B is the height. B stands for P, height of molten metal above the parting surface. Make sense? So P stands for the height of the molten metal only above the parting surface. So what does it mean? For example, if we consider this one, so what should be B in this case? B should be just Q. Don't add 0.6 H1. P only Q. There is no 0.6. Why? Because there is no molten metal in this part. This part, it will be for the core Brent itself. But if we're gonna talk about the molten metal, the height of the molten metal above the surface, the parting surface, there should be only Q. So for this casting, P in the H equation, the big H or the uppercase H, which is the effective height, this B should be Q for the previous example. Like for example, for this case, for this example here, P will be 0. Why? There is no molten metal above the parting surface. For this case, P will equal C. Why? The height above the parting surface is typically the same height as the total height of the casting. For this case, P, it is a portion, there is a value for P. So P, it has a value which is different than C. So what does it mean to calculate H? This should be H, which is the effective height. It's gonna be calculated using this formula, which is H negative P squared over 2C. C, it should be the total height of the casting. B, this is the height of the molten metal above the casting, just the molten metal. This should be the total height. C is the total height of the molten metal of the casting. B should be the height of the molten metal above the parting surface. H is the height of the cube. Then you're gonna substitute, you're gonna end up with H. If you substitute with this formula here, you're gonna end up with the area of the ingate or the gate. Then using this formula, you can calculate the diameter of the ingate. Make sense? This is for step 3. Here about the boring time, as we mentioned, that it should be optimum. High boring time leads to mold erosion, rough surfaces, and excessive shrinkage. It means that it will result in some defects. These are different defects. Mold erosion, it means that you're gonna find some sand particles will be trapped and will be eroded out of the sand mold and will fill into the mold cavity and will result in some defects in the product. In addition, it's going to increase the roughness of the surface of the casting and will result in some excessive shrinkage. Shrinkage, it means that the shrinkage will be high and the casted product will be obtained with less dimension than it should be. Low boring time, it will not permit for the complete filling of the mold cavity, because the molten metal will cool down and it won't gonna able to, and the fluidity of the molten metal will be decreased and the viscosity will increase, which will not allow for easy flow of the molten metal to fill into the mold cavity. This is because we're already boring the molten metal very slow. And so that's why the boring time, it should be optimum. Basically, the boring time, it takes like a few seconds, like between 15 to 45 seconds, or it would be 1 minute, depending on the size of the casting itself. This boring, so since it depends on the casting size, the boring time here, it is a function of G. What is G? This is the gross mass. As we do have bigger castings, it's gonna take longer time in terms of pouring, but it is a factor that should be considered that depend on the material type. For example, like as we mentioned for steel, it is 1.5 as a constant. Then the next step basically is just to calculate the runner dimension. What comes after the ingate calculation, we can calculate the runner, and the runner dimension, basically all the dimension for the runner and the down screw, they are depending on the area of the ingate that we just calculated. For example, for pressurized system, and we discussed before, a pressurized system, it means that you just gonna push the liquid metal to fill into the mold cavity, or you may have non-pressurized system. For pressurized system, we're gonna consider that the area of the runner, it's gonna be the 0.75 times the area of the ingot that you just calculated above over 0.5. But for the pressurized system, you're gonna consider the area of the runner equal to the area of the ingot. Then once you calculate the area of the runner, you can come up with the dimensions of the runner. We said that the runner is gonna take a trapezoidal shape. It will have a width from the top, another width from the bottom, and there is a height. This trapezoidal shape, we said that we are making the shape to avoid trapping and bringing more air inside the mold cavity. So that's why it is commonly that we are using a trapezoidal shape for the runner, and depending on the area that you got, whatever it is, pressurized system or non-pressurized system, you can find the area of the runner. So using the area, you're gonna use this column, use the area that you calculated AR for the runner here, then you just gonna pick the dimensions depending on the given area. So for example, if the area is up to 2 centimeter square, because the unit here is centimeter square, so the dimensions will be 14, 10, and 17. If it is up to 8 centimeter square, so it's gonna be 27, 20, and 34, and so on. This is for the area of the runner. The next step is just to calculate the down sprue diameter. We said that the down sprue, it has a trapezoidal shape, a taper shape, I'm sorry. So it have tapered shape. This is for the down sprue. So it's gonna have a diameter from the top. This is the diameter of the down sprue from the top. And there is another diameter of the down sprue from the bottom here, right? So the area of the down sprue, the area of the sprue from the bottom, it should be area of the ingot that you calculate in step 7 over 0.5 for pressurized system, or over 2 for non-pressurized system. Then once you calculate the area at the bottom, you can calculate the area of the down sprue from at the top using this relation. This relation, we got it from the Euler-Bernoulli equation, and we're gonna discuss this later. So the area of the down sprue from the top is gonna be the area of the down sprue from the bottom times the square root of h over ht. What is h and ht? H, it should be the cube height that you calculated in the step of the flask design. Step 6, we already got this in the cube height. ht, this should be constant, which basically we're gonna consider this value. It is not just constant, it should be like related to the boring cup. This should be related to the cup height. In case that this cup height is not given, we're gonna consider it like 50 millimeter as a height, right? It is related. This is like the difference between because there should be a boring cup here in this area. So this should be the boring cup. So this should be the HT. You kind of, right? So this HT, if not given, you're gonna consider it 50 millimeter for the boring cup. And as I said, it is related to the boring cup here. You can directly calculate to end up with the area of the down sprue at the top. Then once you calculate the areas, you can end up calculate the diameter. The diameter of the down sprue at the bottom, it should be the square root of the area of the down sprue at the bottom that you got times, just do the conversion here. It should be the area, it should be times 4. Yeah, typically like what we did here, it's gonna be 4 times 4 over pi. So it's gonna be times 4 over pi. Times 4 over pi, you're gonna end up with the diameter of the down sprue. Once you find the diameter of the down sprue, don't forget the L of the flask. The length of the flask, you got it as a number plus ds, right? So you're just gonna plug this value here and then find the standard length of the flask. This is the thing that you skipped in step 6 for the flask design. So these are the first 9 or the main 9 steps that we're gonna consider for the design of the mold, of the sand mold. As for the 10th step, which is the riser design, We won't gonna include this one in the design of the task, but this is one of the steps. Once you design everything, you're gonna come up to the design of the riser. But for this step, we're gonna skip this one into this type of problems. I won't gonna ask you to design the riser in this or include this step in the design procedure of the sand mold, because we're going to consider this one as a separate problem later, and it will be discussed in other videos. Make sense? So these are the general steps that we gonna have for the design of the sand mold. So that's it for this part. The next video I'm gonna demonstrate some examples on the design, and we're gonna go over these steps one more time, but over a specific example of a product and how we come up with the design of the sand mold that would be used for making this product. Thank you, and see you in other videos.